KT, this is supposed to suggest the phrase knotted torus. And so the picture is roughly like the following. The picture is that, well, if, I've got this sort of bulk here, which is this 3 manifold. And inside this bulk, well, we have these knots that are embedded that correspond to this is corresponding to a non-Archimedean place, that's KV. And then there's a deleted tubular neighborhood around it that surrounds it, which is this KTV, this knotted torus. And so this knot is meant to be a one-dimensional thing. The knotted torus is meant to be, at least up to homotopy, a two-dimensional thing. And the manifold itself is meant to be a three-dimensional thing. And so where does this dimension count come from? So first I want to just try to explain where the dimension count comes from. And so let's start with the knot. So with finite coefficients, if I look at the Étale cohomology of spec FQ, of spec of a finite field, then that cohomology is precisely the same cohomology as the cohomology of a circle. In fact, you can say something that's a little stronger than that. The entire Étale homotopy type of spec FQ is actually it's S1. I'm putting a little hat on this S1 because I have to profinitely complete everything in this context. So it's a profinitely completed S1. So what does that mean in practice? It means that if I try and compute the Étale homotopy groups of spec FQ, well, then in degree 1, then I'll get a Z hat, and in all of the degrees I get a 0. And so this is a good motivation to think of the knot, to think of the submanifold corresponding to this place as a circle, as an embedded S1. Okay. So now what about that deleted tubular neighborhood? Let's go up in dimension.
May I ask a naive question?
Of course.
So in the Étale cohomology case, is there an action of the Galois FQ bar over FQ, or just the Frobenius basically in this case?
Well, this, I'm just looking at the Étale homotopy type of spec FQ itself, not of something larger, not of spec FQ bar. But if I look at if I look at spec FQ bar, then that's acting as the universal cover of this spec FQ. And the Galois group, or the space of deck transformations for that universal cover, is exactly Z hat.
Right, it's the...
And that Z hat, what is that Z hat? That's exactly, it's got a topological generator, which is the Frobenius.
Mm-hmm.
Yeah.
Cool, okay. Thanks.
You have. Okay, so let's thicken it up and then remove it. So we'll look at the deleted tubular neighborhood of that knot. And what happens? Well, that corresponds to taking this sort of completion. So this is going to be, for example, maybe a finite extension of QP. More generally, what I'm going to say now applies to any non-Archimedean local field. And so if we have such a thing, and if we have a GE module A, a Galois module, this is the absolute Galois group of E, then Tate local duality is a perfect pairing between, on the one hand, you've got the cohomology of that Galois module, and on the other hand, you have the cohomology in negative degrees of this kind of dual. And we're going to say that these are Pontryagin, these are finite abelian groups, and these are Pontryagin dual to each other. And what's this dual? Well, this dual is given to you by mapping into a kind of dualizing object. Mu here refers to the roots of unity. This is the Galois module given to you by the roots of unity, but I'm shifting it by 2. And this 2 is the dimension 2 of our knotted torus. This is precisely that 2. So this is why we think of this thing as a surface. This is a two-dimensional duality. I mean, I guess I could have written this, if I wanted to be more classical, I could have written this by writing a 2 here and marking this part out. It's the same sentence. So, but this is a two-dimensional duality on this space, and that makes us think that this is meant to be a surface. So the knots are one-dimensional. The deleted tubular neighborhoods of the knots in whatever bulk there is are two-dimensional, and then there should be a three-dimensional duality telling us about the entire space, about all of MF. And there is. And this one's a little more complicated, and we're going to use that complication to our benefit in a little while. But here's the story. So if we have a constructible sheaf F on the atoll site of spec OF, then we're going to get a three-dimensional duality. But in order to state this three-dimensional duality, I have to make a couple of kind of slightly awkward assumptions. I have to assume that either F has no real places, so that F is purely imaginary, or else I have to assume that our sheaf doesn't have any two torsion. So one of these needs to be true for what I'm about to say next. And then the sentence is the global duality theorem. And I've ascribed it to Tate, Artin, Verdier, and Mazur because those are the places where I know that it's written down. But I'm prepared to be corrected on this. In any case, it's a perfect pairing. And how does the perfect pairing work? Well, it's the compactly supported cohomology. I'll explain what this compactly supported cohomology is in a second. Of spec OF with coefficients in F. And I'm pairing it with, again, I'm taking some dual of my F, and I'm looking at the negative cohomology of it. So once again, I'm expressing this as the Pontryagin dual of this. And here, what is this dual? This dual is given to you by taking maps from F into GM shifted by 3. Right? So once again, this 3 here is the three-dimensional part of the duality that we're talking about. One funny point here is that this is not a constructible sheaf. GM, in some sense, the dualizing object that appears here is not an object of the category. This is actually a kind of funny issue that can be addressed in a couple of different ways, but it's interesting to note. But okay, I need to say something about this C here.
But can you replace GM by Q mod Z twisted by 1?
Depending on what you mean by Q mod Z twisted by 1, the answer is yes.
The torsion in GM.
Yeah, you can replace it for some purposes with the torsion in GM. That's right. It's actually there's a more sophisticated variant of that same thing, but I wasn't going to talk about it.
Okay.
Yeah. So what's this compact support? This compact support, well, for every Archimedean place, I'm supposed to add a point, right? The MF was supposed to have an extra point, and it's supposed to be, I'm going to say, a geometric point, which is to say that it's not supposed to have any interesting arithmetic at that point. So you're going to add this point, but its deleted tubular neighborhood is supposed to be the classifying space of the absolute Galois group of the completion. So what happens here? Well, if it's a real place, then this is the real numbers, and I'm looking at BC2. If it's a complex place, then I'm just looking at a contractible space here. So in some sense, this is kind of a strange thing to do, but it's not going to change the homotopy type at all in the case of the purely imaginary situation. But if you've got real places, then you get copies of these things showing up. And actually, it's exactly the presence of these things that makes us have to kind of duck the situation with two torsion in our coefficients. And we'll come back to this a little bit. Okay, so but the upshot here and the real meaning of this story here is that we've got ourselves a three-dimensional duality theory, which requires us to compactify spec OF in some sense, in some very homotopical sense. But nevertheless, we have ourselves a nice three-dimensional duality. And so we really want to think of this thing now as a three-manifold. And we want to think of this as a three-manifold with all of these embedded knots coming from the non-Archimedean places. So the extension to this idea comes as follows. If you think about sort of invariants that happen at the level of low-dimensional topology, serious progress is made in low-dimensional topology only once you involve field-theoretic ideas. For example, the Jones polynomial is most naturally something that comes from Chern-Simon's theory. That's where you see its symmetries correctly. So the idea is that we want to sort of import that technology into this setting. And these are the arithmetic field theories. And so the hope is that once you have access to some of these field theories, that it'll do some work to organize a lot of the difficult things that we would all like to see. So one of the things that appears in Kim's first paper about this is these conjectures of Kato and Fukaya-Kato on L functions. And the idea there is that you know, an L function should really be thought of as a section of a certain determinant bundle over the moduli stack of constructible sheaves on MF. And if you have access to something like that, then, well, then a lot of important conjectures of number theory follow. Another example of this sort of thing is that you might hope to import something like and this is even more speculative, you might hope to import something like the field theories that control geometric Langlands into the arithmetic setting. And why might you want to do this? Well, we're already aware of some success in this regard. So for example, the program of Fontaine and Fargue already allows us to use sort of geometric techniques to prove local Langlands. So you might hope that a sort of similar strategy is going to allow you to access global Langlands. Again, that's completely speculative, but it's some motivation for actually thinking about these field theories seriously. So then I think there's two.
Before we're going to field theories on MF, there's already an L function associated with the F. It's a Dedekind zeta function.
Yes, that's right.
Is that supposed to somehow show up in the geometry of the three manifold?
Do you have a conjecture about that, Minhyong? I don't have a conjecture immediately about that.
Sorry,
Oh, maybe.
what was the question again? So yeah, it was phasing out slightly.
It's well, there's a natural L function associated with the number field, basically the Dedekind zeta function of F.
Right.
Does that is there any geometric interpretation of that in terms of the three manifold?
Oh, sure. I mean, the Dedekind zeta function is associated to the trivial sheaf, twists of the trivial sheaf. So it should be just, so somehow when you're considering complex representations, every sheaf comes with a one parameter family of shifts coming from these Hecke characters, right? And so the Dedekind zeta function is just the section of the determinant line bundle along that one parameter family. It's not a conjecture or anything, that's just a fact.
This is okay. And so what about special values of this L function? Are they, one can consider them as invariants of the three manifold?
So yes, sure. So well, they are. I mean, no matter what way you look at it, they are. So, but if your question is there a kind of field theoretic interpretation of that? Very roughly speaking, if you would look at just the class number formula where the value at 0 where the class number shows up, so those values are very well, they're analogous, and maybe you can say something slightly better than just being analogous. They're like the way, well, they're very roughly similar to Casson invariants, for example.
Cool.
Or abelian Casson invariant.
By the way, is it?
Oh.
So are there explicit examples for imaginary quadratic fields?
Explicit examples of what?
Imaginary quadratic fields, because well, in that case, I know that the special value is given by the Dirichlet class number formula.
The special value at 0, of course, yeah. That's right.
Yeah.
And what is the three manifold in this case? As in, what is the rank of its H1? The H1 we've been considering.
Well, in this context, it's more like the torsion of H1, yeah, but that will just be the class number.
Yeah.
Okay.
By the way, Minhyong, it seems that I can't send a general chat message to everyone.
Oh, is that right?
It's a setting, I think. I was going to mention it might be interesting to think about this in terms of Denninger's dynamical systems, but I don't want to get us too sidetracked.
Yeah, it's possible. Yeah, sorry, I'm not sure why you can't send the chat.
It's an option you can change anyway.
I see, yeah. was usually possible, but okay, yeah. Sorry, I'll look into it.
So I just want to say that there's sort of two approaches that you can take to this. So there's this sort of mystery about what these field theories actually are and how they behave. And I think there's sort of two attitudes that you could take as a result. And one attitude is you could use this as a kind of idea generator or even conjecture generator, where you sort of produce some ideas that you can then check using more traditional methods to see whether or not these things are true. I mean, you don't spend any time getting bogged down about defining or constructing these field theories in any precise sense. And I think that's sort of one end of this kind of picture. The other end of this picture that's the picture that I want to talk about is that you could instead try to define some of the salient structures that show up in this idea of arithmetic field theories. So, you know, for example, you could try to actually make sense of the algebra of observables attached to an arithmetic field theory. And the act of trying to write down that structure precisely well, it turns out to have some interesting consequences. So that's the thing that I'm going to tell you about today. So, okay, so the eventual goal in my case is to try to define factorization algebras on this mythical three manifold and then construct the relevant examples. But in order to define factorization algebras, so these are the algebras that are supposed to appear as the observables for some eventual field theory. But in order to construct the factorization algebras, those factorization algebras are going to be described in terms of constructible sheaves on some Ron space. So maybe a challenge that I want to issue to the room is to write down the Ron space of MF. And what do I mean by that? Well, I don't really necessarily need the full power of the Ron space itself as a topological space or anything. Maybe all I really want is I want you to describe it well enough so that I can write down its category of constructible sheaves or constructible co-sheaves. And if you do that, then I'll have considered that a success, and we can actually start trying to construct such things. And so that's the question that I want to try and address. So sort of two things happening here. The first thing that's going to happen is, well, this idea of just describing it well enough to describe the category of constructible sheaves. My claim is that that's the construction of a certain homotopy type that will be attached to the Ron space. And the second thing that I'm going to try and argue is that constructing that homotopy type in the case of MF itself already provides us with kind of an interesting story. So let's talk about MF for a little while. I haven't told you what it is. I've just sort of told you roughly how I'd like to think about it. So given that I'm a homotopy theorist, I want to kind of approach this thing by kind of taking better and better snapshots of it and see if I can resolve my intuition on how it behaves. So for the 0th approximation to this thing, I want to contemplate the Étale homotopy type. And you'll see that this isn't a very good approximation, but it's still worth contemplating. So what is the Étale homotopy type? Well, it's a homotopy type. It's actually a profinite homotopy type, and it's defined so that when you take its pi naught, you're just getting the set of components of your scheme. X is, say, a scheme or a variety or an arithmetic object. And pi 1 is, well, it's the Étale pi 1, which means that it classifies Étale covers of your scheme. And then this homotopy type is arranged so that its higher cohomologies with coefficients in some local system, its higher cohomology is the Étale cohomology with coefficients in that local system. And here I can be quite agnostic about what kinds of local systems I want to take. As long as they're Étale local systems, I'm happy. This is a perfectly valid formula. So that's the kind of information that that the Étale homotopy type stores for us. And so then the question is, well, what does it look like in examples? So let's do some of these computations. Well, so first, the simplest example is that if I just take spec of a field, then I get the classifying space of the absolute Galois group of the field. And if I take a scheme of finite type over the complex numbers, and I take its Étale homotopy type, then that's the same as what you get if you take the C-valued points of X consider that homotopy type, and then, well, I have to kind of profinitely complete it. And this will recover the Étale homotopy type. So this is telling you that the sort of topological intuition you have about a variety over the complex numbers agrees with what the Étale homotopy type is producing for you. Perhaps most interestingly for our purposes is that if I take spec Z and I take homotopy type, I don't get anything tractable. This is a consequence of the fact that Q doesn't have any unramified extensions. That tells you that the pi1 is trivial. And then arithmetic duality tells you that you don't have many options for what the other homotopy groups can be. And so you end up with, and using that in Hurevich tells you that you end up with a contractible space. If I take the Gaussian integers, it's rather more interesting. It's a cofiber of a degree 4 map from S2 to S2. So this is sort of 3-manifoldy. It kind of has cohomological dimension 3, but it isn't really the sort of thing that you'd like to call an oriented 3-manifold. But nevertheless, that's the computation. So there are some issues with this as a base for trying to do arithmetic field theories. The first issue is that this Étale homotopy type doesn't see any of the structures that we've just spent our time talking about. It doesn't know that there are these embedded knots that we were talking about, these embedded submanifolds, and it has no way to understand the deleted tubular neighborhoods that are supposed to arise in the picture that we drew of our 3-manifold. Perhaps in the same vein, well, global duality, that was a statement about a constructible sheaf on spec of your number ring. So global duality has to do with constructible sheaves. But the Étale homotopy type can't see all constructible sheaves. It can only see the local systems. And in the case of something like spec Z, that means that the Étale homotopy type simply isn't going to see anything. So in the case of Q, we're not going to see any of the structures that we were trying to study when we were thinking about global duality and arithmetic topology. So I'm going to address both of these issues.
Can I ask a question before you move slides?
Yeah, of course.
Is it easy to say sort of what sort of number theoretic observation corresponds to having the non-trivial homotopy groups in the Zi case? Where do they come from, so to speak, in terms of the number theory?
Well, I guess in terms of sort of traditional number theoretic invariance, I think that it would probably have been better if I'd said something about the cohomology of Zi instead. And the non-triviality of the cohomology, I guess, has a more obvious relationship with number theory. Okay. So really the point here is that the cohomologies are non-zero. I guess the fact that the homotopy, I don't know how to interpret the homotopy groups being non-zero in a kind of.
Yeah, but once there's some non-trivial cohomology that forces something about the homotopy type. Okay.
Yeah, exactly.
May I just add that this 4 is exactly the number of roots of unity.
Right. Yeah.
Right. On the other hand, we didn't have, I mean, Z also has a non-trivial group of roots of unity, and we don't see that in its homotopy type. So there's something more going on.
It's for a totally imaginary number field with class number 1.
Oh, right, because that has a real plate. So yeah, that certainly makes sense.
Sorry, so it's for the size of its first homology.
Pardon?
The first is the first homology of this space Z mod 4.
No, I don't think so.
There's a Z mod 4 somewhere. I'm just getting confused about the degrees.
I think it's in degree 3.
Oh, okay. Okay.
If I'm not mistaken.
That makes sense. I just was getting confused about the direction of the.
In degree 2.
In degree 2, sorry. Thanks, Tomer. Okay, so I want to refine this picture a little bit. And so this is what I'm calling the first approximation. So this is the first approximation to that manifold MF. And I want to do it in such a way that it addresses the sort of issues that I've raised. And the idea is to use stratifications to do that. So this is going to be the stratified étale homotopy type. And this is going to be an object I'm going to call gal x. And I'll tell you what kind of object it is in a moment, but it's going to be a thing that we're calling a stratified étale homotopy type. But morally, what is it supposed to do? Well, it's supposed to address the issue that that the étale homotopy type only knows about local systems. That relationship is called monodromy. And we're going to address it by saying that gal x should have the same relationship with constructible sheaves that the étale homotopy type has with local systems. And so this new relationship is the thing that we're calling exodromy. Okay, so but what kind of object is this going to be? Well, there's a theorem by my graduate student, Peter Hain, who noticed that the equivalence that we use in homotopy theory all the time between homotopy types and infinity groupoids, that equivalence actually extends to an equivalence between stratified homotopy types and infinity categories with the property that the only endomorphisms are actually equivalences. So these are sometimes called, I think Peter calls these layered infinity categories. So these are infinity categories that don't have any interesting endomorphisms except for the equivalences themselves. So this is a kind of a difficult theorem, and it's sort of a distraction from the main point of the talk today. But the point that I want to make here is that there's a sort of meaningful homotopy type, and you can express that meaningful homotopy type very efficiently by just writing down a category or an infinity category. And if that infinity category is well behaved, then you can really treat that as a homotopy type. And there are ways to extract sort of the things that we like about stratified spaces up to homotopy from such an object. And that's the effect of what Peter's proved. So now what's the story going to be? The story is going to be that I'm going to take a scheme X and I'm going to write down a category. It'll turn out to just be a 1 category, so I don't need all the fanciness with the number infinity. It's just going to be a 1 category. And that 1 category is going to play the role of my stratified homotopy type. So here's the definition. And one of the things that I think is quite pleasant about this, by the way, is the fact that when you ask someone, hey, what's the étale homotopy type of a scheme? Write down the definition. You hem and haw and so forth, and you make some complicated construction, and it takes a minute. But here I'm actually just going to tell you what the objects and the morphisms are directly, because it's just a 1 category. It's a profile category, but it's just a 1 category. So the objects are geometric points. So for me, a geometric point means that omega here is the separable closure of its image point in X. So that's an object of this category. A morphism from a geometric point X to a geometric point Y is I guess the right thing to have said was that it's a generalization, although I have trouble saying that word, from X to Y, or if you like, it's a specialization from Y to X. So how does that work? Well, if I have my point X of X and I have my point Y of X, then I can look at the strict tensillization of the local ring at X. I'll denote that by this. This is the strict localization of X at this geometric point. And then a specialization is a lift, phi, from Y to this. That's what I mean by a specialization. These specializations compose, and this defines a nice category for you. And this category is the category that I'm going to call gal. So the objects are geometric points and the morphisms are specializations, or if you like, generalizations. And I'll tell you a few theorems about this category, but first I thought I'd write down some examples. First example is going to be a little unexciting. If I do this to spec of a field, I don't get anything new. I just get the classifying space of the absolute Galois group again.
Yeah. Can I ask a quick question?
Of course.
Is there a simple way to describe the profinite topology on this category from this very concrete description you gave?
You said the profinite topology?
Yeah.
Is that what you said?
Yeah.
Simple? No. Concrete? Yes. Yeah, I mean, it's the same. It's a sort of globalization of the profinite topology that you have on the absolute Galois group of a field. So, you know, it's generated to you by looking at sort of finite extensions of things. That's not a brilliant answer, but it's the easiest one I can give right now.
Thanks.
But when you say it's a profinite category, do you just mean the Hom sets are profinite sets, or is it like the set of objects is a profinite set?
The set of objects is also a profinite set. It is a stone topological space in the category of categories, or equivalently a category object in the category of stone topological spaces.
The last one makes the most sense.
Yeah, no, it really is. It's on both the objects and the morphisms. So why would you expect that? Let me give you some motivation for why you might believe that. So if you think about the Zariski topological space attached to your scheme, then the Zariski topological space attached to your scheme can be regarded as a profinite poset. And that's some shadow of this structure that we're looking at. So that's the profiniteness happening right there. Okay.
Can I ask a really basic question?
Yeah, of course.
Is this category a poset?
Oops, you cut out. Is this category a what?
Poset.
No, this category is not a poset. It maps in a conservative fashion to a poset. And that poset is the specialization poset of the Zariski topological space. So it maps in such a way that every morphism that goes to an isomorphism was already an isomorphism. That's what I mean.
All right. Okay, great. Thanks.
You bet. Yeah, so in this case, it's rather unexciting. So, and if you sort of reflect on it, this is clear. I mean, the objects of my category, these are separable closures of K. The morphisms are specializations, but the specializations can't be very interesting. They have to be isomorphisms. So I'm stuck, excuse me, with just a copy of the classifying space of the absolute Galois group. So let's be a little more exciting. Let's now take a DVR A, and let's take one with residue field K and fraction field big K. Then the way this category looks is starting to be a little different. You're going to have two objects up to isomorphism. You're going to have one corresponding to the closed point and one corresponding to the open point. And the closed point, well, it has a group of automorphisms. That group of automorphisms is the absolute Galois group of the residue field. And the open point has a group of automorphisms, which is the absolute Galois group of the fraction field. And then there's a whole lot of maps going this way from the closed point to the open point, from this object to this object. So what are these maps? How do we understand what these maps are? So it turns out, if you want to sort of connect this to sort of our traditional way of understanding DVRs, it's convenient to actually do something a little different. It's convenient to write down first the space of maps like this, where you say that two maps are connected by a path, if and only if you have an isomorphism here and an isomorphism here that makes the diagram commute. If you look at that space turns out to be the classifying space of the decomposition group. Now the decomposition group sits inside the Galois group of the fraction field, and the decomposition group mod the inertia group gives you the Galois group of the little field. And so we have this map from BDA to the product of these two things. Now, normally, if you think about just the groups, then all of this is defined up to conjugacy, but because I'm kind of being everything here, this map is actually well defined already. There's no base point issues anymore. So you have this canonical map from here into here. And this is really playing the role of the link in the stratified space. This is playing the role of the connective tissue that's taking you from the closed stratum here to the open stratum here. That's what this is. And then a fiber, yes.
Theory?
Pardon?
You said the link.
Yeah, I mean the link in the
That's
sense of
knot theory?
stratified topology.
Oh,
So what I mean by that is I mean it's the deleted tubular neighborhood of this closed subset of the bulk. Does that make sense?
yeah. Okay. It just has nothing to do with the word link in knot theory.
No,
Oh, okay.
sorry. Yeah, there's too many links. Yeah, different. Yeah, maybe I'll say it again. I'll say it differently. I'll say that this is the deleted tubular neighborhood, really, of this closed point inside or of this closed stratum inside the bulk. And so the set of maps from a choice of separable closure here to a choice of separable closure here is the fiber of this map over the sort of corresponding point. And so the picture of this is kind of roughly like this. This orange ring here, that's what I'm imagining to be the BG little k, the closed stratum. There's this open stratum, which is this sort of wobbly bit out here. That's the BG big K. And then there's this deleted tubular neighborhood, which is given to you by the classifying space of the decomposition group. And that's the picture that's in my head for how this thing behaves. Okay, and let's do another final example. Well, just as in the story with the Étale homotopy type itself, if you happen to have a scheme of finite type over the complex numbers, then its Galois category is equivalent to the stratified homotopy type of the analytic topology on the complex points of X, where you're stratifying now over the entire Zariski topological space. So here I'm really thinking of that Zariski topological space as a profinite poset. And then once again, I have to kind of fix this up by adding a profinite completion in. Okay, so my claim was that this category that I cooked up is going to have some relationship with constructible sheaves, which is analogous to the one between the original Étale homotopy type and local systems. Oh, but I forgot. I wanted to give another example, which is the Galois category of Z itself. Good, let's do that. So the Galois category of Z itself looks roughly like this. Well, you have all of these one-dimensional, they're circles, in fact, which are BGFPs sitting inside this object. You have the complement of all those knots, which is BGQ, and you have the deleted tubular neighborhood of all those knots, which is BGQP. So the point that I'm making here is that, in fact, this stratified homotopy type is exactly giving you the picture that we were looking for when we were trying to think about the model of this thing as a three-manifold. Almost. Okay, so but what are the theorems? Let's write them down. So there are sort of three theorems that we proved about this Galois category. And the first one is the exodromy theorem itself. The exodromy theorem itself says that if you look at constructible sheaves on X with, well, I put lambda here, but I mean any sort of coefficients that are reasonable can go here. So if you like QL or QL bar, you know, whatever your favorite version of constructible sheaves is, that can go here. And those are equivalent to continuous functors. So I'm keeping the topology in play here from this Galois category to perf lambda. That's the exodromy theorem. So in this regard, you see the constructible sheaves on any scheme, that category is really just a functor category. Well, at least if you keep the structure in mind. The next theorem is that what we call the homotopy theorem, for lack of a better name, which is that, well, if we wanted to go back and sort of reproduce our original Étale homotopy type, of our scheme. Oops, I've kind of made a mess here. Let's see, I meant to write that. If we want to try and reconstruct a tall homotopy type of our scheme in the original sense, then we can get it by taking our category and just inverting all the morphisms. So it's really just the nerve of the category gal. And this is the, we have to do this in the profinite sense in order to get the profinite tall homotopy type, but as long as we're careful about that, this is the statement. And then the final sort of main theorem of the book is that there's a reconstruction theorem for lots of varieties. So this Galois category, which is sort of relatively simple, is actually a complete invariant of normal varieties over Q. And in this case, when I say complete invariant, I mean both for morphisms and for objects. So this operation of carrying X to gal X is a fully faithful functor from normal varieties over Q to profinite categories over BGQ with certain kinds of constructible maps. So this is supposed to be indicating to us that this Galois category is actually, it's very knowledgeable about your schemes. A gal of X knows a lot about your scheme. And in fact, in this case, it's even sufficient to reconstruct your scheme. Okay, so this is the sort of surrogate that I want to use as an approximation to MF. And what we see here is that, well, if I'm interested in the duality theorem that was supposed to be motivating my three-dimensional idea, then this might be a good place to start because after all, it knows all about the constructible sheaves. But there's an issue, and the issue is that, well, I was supposed to be taking spec Z or spec of the ring of integers of a number field, and I was supposed to be compactifying it. So the idea in that compactification was supposed to be that I was going to add a new point, which is a geometric point, for every Archimedean place V. I didn't have them in the scheme, so I have to introduce them now. And the deleted tubular neighborhood is supposed to be the classifying space of the absolute Galois group of the completion of my number field at V. But I want to make the point that at real places, this is perhaps not the best idea. So this, by the way, is the classical story. This is the way in which, I mean, it's a reinterpretation of the classical way in which the Artin-Verdier topos is constructed. But it produces quite strange answers. So for example, if I look at this situation, well, I've got the classifying of the absolute Galois group of R, which is an RP infinity. And well, I have here a point and here a point, and I'm forming a homotopy pushout here. So the result here is the suspension of RP infinity, which doesn't look very much like a three-manifold at all. It's the cohomology of this thing is in no sense a three-manifold. Its problem is sort of localized at the prime 2 when you think cohomologically. And that localization at the prime 2 is exactly the issue that you saw when I was trying to rule out the possibility of having constructible coefficients that had 2 torsion or 2 to the n torsion in the coefficients. So this is an issue that we've already kind of addressed by just avoiding it. But if we want to be careful about this, if we want to construct this thing seriously, it seems a little strange that we end up with this thing. So there's a way to fix this. And here's the idea. This idea goes to Fontaine and Fargue, and more recently Schulze, and I think others as well, which is that this classifying space of this absolute Galois group is really a shadow of a more sophisticated object. You can really think of geometrizing the absolute Galois group of the reals, and you geometrize it using the twister line. What I mean by the twister line is I'm going to take the Brouwer-Severi variety attached to the Hamilton quaternions over R. So this is what you get by taking P1 and you take the operation Z goes to -1 over Z bar and you descend down to a real algebraic variety. And now that étale homotopy type of this thing is an RP2. So for my purposes, this is already very convincing, because now that I've got an RP2, this must be the right thing, but there's actually more sophisticated reasons to be convinced of this. But if I replace systematically my BGR with RP2, then I'm going to get a different kind of push out. And here's the push out that I get to look at. Well, I still have point here and point here. I didn't do anything about that. But here I've got RP2. And so here what I'm going to produce is the suspension of RP2 up to homotopy. And this looks, well, it's still not what you'd call a compact 3 manifold necessarily, but it's a heck of a lot closer. It's at least got cohomological dimension 3. And so this is a much more promising object. By the way, I'll just make a little sidebar here, which is that it would make sense also to take the BGQPs that are appearing as the sort of deleted tubular neighborhood of those knots and replacing those homotopy types with Farg-Fontaine curves. I don't precisely know how to do that, mostly because I don't know what the étale homotopy type of the Farg-Fontaine curve looks like. I know what its fundamental group is, but I don't know more. So it's only ignorance that's stopping me from doing this. I'm just not sure. But in any case, here's the theorem, and I guess this is going to be the only theorem in the talk. Sorry?
Is the étale homotopy type of the Farg-Fontaine curve not just the same as that of QP?
I don't know. I know its pi1 is the same as that of QP.
Okay.
Are
you also
does
thinking
somebody
maybe
know?
of But then also, even if it is the same, the stratified homotopy type is probably very different.
I would assume that it is, yeah.
Then you have all these points.
Exactly. But I would also be worried about that well, look, maybe we should talk. I have a different comment about that, but maybe it's not relevant right now. But yeah, so I mean, if somebody knows what the étale homotopy type of the Farg-Fontaine curve, just in the case of QP, is, I would be delighted to learn something new this way. It's only ignorance that's stopping me from trying to understand this. In any case, let me give a theorem now. So I'm going to compactify gal OF using this strategy. So the idea here is that at the real points, I'm going to take the twistor line, the real twistor line, and at the complex points, that I'm going to take the complex twistor line. So that's going to add either an RP2 or an S2 as the deleted tubular neighborhoods of the points that I'm adding on when I compactify. So I'm going to construct this compactification of gal OF. This is really just as a stratified homotopy type, not more right now. But the stratified homotopy type is sufficient to know about the category of constructible sheaves. So I'll use that. And then the theorem here is that there is a perfect pairing from the cohomology of this compactification with coefficients in F. Well, it's the same story as I told at the beginning, into this F dual, where F dual here is, I'm again homming F into GM shifted by 3. Now I can allow my coefficients to be a lot more general, however. So now the coefficients can be things that are exceptionally general, like pycnotic abelian groups, or, well, anyway, even pycnotic spectra and stuff like that. So these things can be much more general now. And in particular, there's no fiddling with the prime 2. This is just now a correct duality statement on the nose. And this is the circle.
Sorry, so is there also no imaginary hypothesis?
That's right, yeah. So I don't have to do that thing where I either make myself purely imaginary or I make myself avoid the prime 2 in my coefficients. I just allow everything.
Thank you. Interesting.
Yeah. So this is the theorem that we can prove. It's still perhaps a little unsatisfying because it doesn't involve the sort of more sophisticated fix to the deleted tubular neighborhoods of points, but nevertheless, this duality theorem is true. And so we sort of think of this gal OF bar as a good approximation to this gadget MF. But that wasn't the mission that I started out with. The mission that I started out with was to construct the Ron space of MF, at least well enough to identify its constructible sheaves. So I've constructed something that looks like maybe a good approximation to the stratified homotopy type of MF itself. But what we'd really like to do is construct the stratified homotopy type of its Ron space. And of course, that's going to depend on much more than just the stratified homotopy type of MF itself. It's going to depend on some geometric structure.
Sorry, Clark?
Yes.
And the reason we want the Ron space is because you wanted factorization homology. Was that the reason?
Yeah, I'd like to construct factorization algebras, which should work as the observables for one of your quantum field theories.
Okay, I see. Mm-hmm.
And I mean, there's several problems with the idea of constructing this. I mean, first of all, the strata are supposed to look like configuration spaces of points inside MF. So that involves doing something like taking MF cross MF and dividing out by the symmetries. But that cross there should correspond to something like a product over a deeper base than Spec Z.
Right.
So, of course, this starts to get into very conjectural territory. But there are examples where we know how to do those kinds of constructions, namely Schultz's theory of diamonds, Schultz and Weinstein's theory of diamonds, allows us to perform things like the product of SPD QP with SPD QP, now regarded as things over F1.
Right.
So if I look at the product of these things in diamonds, then I should be able to construct such a thing. So what I'm trying to say here is that I can't just take the stratified homotopy type of MF itself. Instead, I need to work with sort of geometrizations of these pieces. So and we know something about this. So in the case of the closed strata, I know that I should be looking at S1s at the Archimedean places. Sorry, that should say at the non-Archimedean places. And points otherwise. And we know more about the deleted tubular neighborhoods thanks to the Farg-Fontaine curve and the twister lines. So in a sense, I guess what I'd like to propose, and I guess I'm proposing this without having really fully thought about it, but what I'd like to propose is that one can construct what sort of looks like a boundary Ron space for the thing that we're really trying to construct. This thing will have the information of the Ron spaces of, well, just some S1s that are lying around, and Ron spaces for the Farg-Fontaine curves and twister lines. And this could be enough to construct things that are sort of the boundary theories from some of the theories that Minhyong's trying to construct on the bulk. And it would be interesting to try to understand, for example, whether there are any meaningful examples, for example, of chiral algebras on the Farg-Fontaine curve. I don't have the expertise necessary as a homotopy theorist to answer that kind of question, but
Sorry,
I wanted to put, yeah.
I have a question just about the geometric intuition. So where the Archimedean points are just supposed to be points, right? So then the tubular neighborhood of a point, deleted tubular neighborhood, is up to homotopy a sphere. And I guess is that related to the idea that the twister line is geometrically P1, which is a sphere?
Yeah, for a complex place, that's right. Yeah. And for a real place, it's quite strange to think about having a point in a 3-manifold and its deleted tubular neighborhood looks like an RP2, but that's the structure that you get at the real places.
And the fact that the twister line is twisted reminds me of, I mean, Minhyong has this comment in one of his papers about how, the complement of the tubular neighborhood shouldn't really be a torus, but it should be some sort of twisted torus.
That's right. That's right. And it's kind of ludicrously twisted. I mean, sort of at, the orientation sheaf isn't even a finite type, right? You have to include everything.
Right. And then I would just, in terms of this S1 versus point dichotomy, I mean, that really makes me think of Denninger's dynamical systems.
So you'll have to educate me on Denninger's dynamical systems, because I haven't read enough.
It's supposed to be a better way than just a 3-manifold to think about in a number rings.
I'd like to think about how to integrate that with this sort of homotopical perspective that I'm taking here. I mean, in some sense, the picture that I've developed here is so blurry that you couldn't possibly see something as refined as a dynamical system. But I don't know.
Or I wonder if you could sort of think about the Rand space of the related to the dynamical system and get intuition for this. But we should talk maybe.
Yeah, that sounds interesting. Yeah, I don't know. So that's all I have prepared today.
Yeah, thanks very much. So as usual, we'll move on to the question session, which can continue as long as the speaker has energy.
I wasn't up too late watching the results come in. I'm okay.
Right. I'll have to leave fairly soon, but I'll leave this open that
Okay.
anybody who wants to keep chatting. So are there any questions at the moment?
I have a question.
Go for it.
So, so I was thinking about the fact that it's a complete invariant. I forgot how you call it, Reconstruction Theorem or something like that.
Yeah, this guy.
Yeah, and I just realized that one thing that you get out of it that is that, right, if you have one of those Galois categories over BGQ, then you can, for example, you can define the groupoid of n-dimensional vector bundles on X in terms of this gal by essentially mapping it to GLN, to BGLN.
Yes, that's true.
Yeah.
That's right.
So there's kind of an so you can get kind of coherent kind of invariant for an arbitrary such Galois category. So you can ask questions like for example, you can define the K theory of such a thing and ask if it satisfies, and you know what an open and closed decomposition is, because that's just a map to a small poset. So you can ask things like, I don't know, like the localization sequence for arbitrary. Like I guess
that's a fun idea. I love that idea.
I'm wondering is to what extent do you think that if I just take one of those for finite categories that has a conservative functor to a poset, together with a map to the absolute Galois group of GQ, the resulting thing that I'm now kind of can think about a weird algebraic variety would still behave like a normal algebraic variety in the sense that certain theorems would still be true. This was just one example of kind of thing that I wonder if you really get kind of generalized algebraic varieties somehow.
Yeah, I mean, I guess the question is whether or not you have that sort of the wrong way recollement on quasi-coherent sheaves, and that's where the K theory long exact sequence comes from.
Yeah.
So I wonder, is there some formal reason to expect such a recollement to happen with your definition of coherent sheaves or of quasi-coherent sheaves?
I think you have a leg to stand on. It's hard to predict exactly what's going to happen, but right, like the way you're going to define vector bundles, right? You need to say, okay, I need to choose some open cover, which you know what it means, and then map from the intersection to GLN, which you use this reconstruction theorem.
Yep.
And then so at least like it's. So, for example, restriction of a vector bundle is a vector bundle somehow in a very direct way here, and yeah, I don't know. It's of course only one version of that. I'm just kind of very curious by the, in some sense, this functor is clearly extremely not essentially surjective.
Yeah, right. There's all these like beasts out here. Yeah.
But it's kind of interesting to ask, okay, if you're trying to add some of the missing objects, are they just completely stupid? They're just kind of, or are there actually in some sense new geometric objects that behave close enough to the original objects so that they kind of are allowed to be embedded in this theory?
I mean, you can even be more. I mean, so okay, so one way to think about this reconstruction theorem, let's just think about the case of curves for a minute. One thing that it's saying is that if you take you can take a curve of, say, of genus G, and you can extract from it its the corresponding Riemann surface, and you can look at that Riemann surface stratified over the Zariski topological space. But I mean, for curves, that's not any real information, right? You just have some closed points and a generic point, and it's just combinatorics. And you can put a Galois action on that whole thing, and that's sufficient to reconstruct your curve. So you could ask, all right, let me give you all of that data, right? I'll take a genus G surface and I'll stratify it over the same poset as you always choose for a curve, and put a Galois action on the whole thing. I guess it's really hard to write down that much data. But suppose you did,
Wait,
that would be some sort of disembodied curve or something.
But is it right? It's not. Wait, it's. You need to be a little bit careful here, right? Because the poset is like you're not allowed to remove any finite set of points. You need to remove only points over Q bar. You're not allowed to remove R transcendental points.
That's right. That's right.
It's kind of always
Right.
very.
Actually, that issue comes up in like one of Mochizuki's theorems in Edinburgh geometry. Where, right, you're reconstructing things just from the fundamental group where you just delete the algebraic points.
Right.
Clark, could I ask a question?
Yeah, of course.
So here you have your spaces are, you said, zone categories or something like that, right?
Mm-hmm.
So you've put schemes into this larger category. Now, these are, I guess, supposed to be actually like spaces and not just spaces up to homotopy somehow, right?
Yeah, they're spaces. There's spaces along with stratifications up to stratified homotopy. That's right.
Right. I was wondering if it makes sense inside your category, is it possible to have something like a cylinder with two boundaries that are finite fields?
Oh, you've asked me something about this before, haven't you?
I think I'm asking again, but
with two different finite fields. That's the hard part.
but how about even a disk with one finite field as a boundary?
The finite field is a boundary. See, that's the thing that I don't know how to do. I mean, so in this category, you can certainly construct something with that shape, just kind of, because you have a lot of room to just do things as you see fit. So you could build something formal, but I wouldn't expect that formal thing to have any arithmetic content unless you. Yeah. How do you get from FQ to FP? That's the real question.
Right. You see, I think you know the reason I'm asking, just to speculate a little bit. If you can do things like this, you can start from a modular tensor category, for example, and construct an arithmetic field theory.
Yeah, exactly. And actually, I mean, when I first learned about this sort of arithmetic field theory idea, I spent a long time trying to think about how
you might do something like this.
how Bordisms might operate. And what I concluded was that I wasn't going to be clever enough to come up with something. And so that instead what I was going to do was I was going to try to use the factorization algebra approach to sort of seeing these things.
I think you explained that one. Yeah. The problem is we have these very large Bordisms, right? Like entire rings of integers with two primes like that. But we don't have nice simple Bordisms.
Yeah, we have these sort of monsters that are kind of big and profinite, but.
So you can do sort of like a chain, like what's it called, categorical chain complex kind of situation. Like, can't you just, you can kind of define the dimension of one of your things as like you know, you can look at the chain just in the normal way. You can look at a chain of descending subsets, closed subsets. You know what I'm saying? So you can.
Yes.
So does that machinery not just give you a sort of type of Bordism, because you can kind of define categories with or manifolds with corners? Is that not automatic?
Something is the boundary of something, right?
Yeah, how do you, that's the, I don't know how to say the word boundary correctly.
That's the thing.
You can't say like all things that only have morphisms going into them. You know,
let me just think about that. Oh, I see. You're trying to say like, oh, interesting. You're trying to say that like that's some sort of cofinality type thing at the categorical level. That's interesting.
I'm not sure what I'm saying. I guess I'm saying if you have one of these categories, then the boundary should be like all strat. I guess that's not really true necessarily. I was just trying to say you take things that only that have like out degree 0 or whatever, or in degree 0. But that's not a real. I don't know. It's not really the boundary. It's just that's all of the strata.
Yeah, right. That's just going to give you everything. But yeah. I don't have a compelling. Maybe I'll just say one thing, which is that you know, one thing that's kind of tricky about this story is that it's difficult to see. You know, so for example, take one of these varieties over Q. So the question of whether or not that variety is proper over Q is, at least in theory, a question that you ought to be able to answer just from this category. And I don't know how to do that. I don't know how to answer that question just from, I don't know how to characterize the things that are proper from just this category. And this is a little bit like what you're asking, right? I mean, when you think about the boundary of, you know, you think about what you would add in a compactification or something. And I don't know how to characterize that sort of in a category theoretic way. Yeah, it would be interesting to learn something about that.
So what if, let's say you want to move from Spec F2 to Spec F3 in Z. You want a boundary between those two things.
Yeah.
So you know, I don't know what are the conditions you want from your Bordism, but one somehow candidate is the number 2/3 somehow. Because so let me try to convince you that that's not such a crazy notion. So for example, let's say you want to describe the homology groups of a number field. You know, let's say a totally imaginary number field. You don't want to kind of. So there's a very simple. So what you're going to find is that the second homology are exactly the units, and the first homology is exactly the class group. But if you kind of try to prove it, you will see that the way you prove it is because you get that there's just a canonical complex describing it, which is the complex of invertible elements in the field mapping into divisors. That's your chain complex that computes the homology. The kernel is the second homology. The co-kernel is the first homology.
Yeah.
So it really does look like what happens is that you have, you know, a rational function, a rational number is a board, and this is also something that we know from algebraic geometry somehow. Like you can think about, you know, rational function. You know, a rational function is something whose boundary is the divisor. So I don't know if it has enough structure somehow, but it's but from the point of view of the computation of the homotopy type, you really get that you know, you have a circle for every prime that gives you this Z in the divisor class. It gives you a cycle, and the relations exactly tells you that you have a two cycle combining things, the positive part and the negative part of a divisor of a number.
Yeah.
Maybe it's not structured enough somehow, right? Like, what are you going to do with two-third? How are you going to use two-third to move from between 2 and 3? It's kind of stupid, but I don't know. But it is in some sense something that it is kind of a two-cell gluing those two circles. If you look what it does in homology and how homotopy happens.
Right.
I have a comment. It's probably not directly related. Of course, you could consider not just a single prime, but a collection of finitely many primes together, and each one of them would correspond to a knot, and these things together would correspond to a link.
That's right.
Consider a link complement. So this manifold would have a disjoint boundary. Each boundary component would be, I guess you guys call it a super twisted torus, but the number of these tora would obviously be equal to the number of primes you take. So this manifold, this three manifold, is a cobordism between these boundaries.
That's
so in
right.
particular, if you just consider two primes together, then you would get a three manifold, which is a bordism from one knot to another knot. Well, to one, you know what I mean.
Yeah.
So logically this occurs, but I have to go and I have really basic questions, and I don't want to disturb the super hi-fi conversation. So
ask a super basic question. I don't know the answers to the hard questions.
Yeah, great. Well, one, I was just thinking of the most basic invariants of a knot complement in a three manifold. And the first thing is the knot group, or the pi1 of the complement of the knot.
Yeah.
And it just, I mean, that determines how complicated the knot will be.
Yes.
I mean, how would you, is there any way of translating it into arithmetic? How?
Absolutely. It's the Galois group corresponding to the maximally unramified extension, unramified at the prime you away from the prime you cut out.
I see.
So yeah, I mean it's literally true. It's I don't know, where do I have room here? Yeah, it's literally true. So you can take, so you're saying take pi1 of, let's just start with just spec z. I won't bother compactifying, and remove your prime.
Mm-hmm.
And I mean, if you do this with the Attal thing, then this is the Galois group of the, I never know what the right notation for this field is. I'm not sure what the right notation that people use is, but this is the sort of the maximal extension unramified away from the prime p.
Okay.
And so this is absolutely something you want to think about. So one thing, I mean, so there's a if you like this kind of thing, then there's a book where you can look at all these things by Morishita, who I guess isn't here. Otherwise, he would be the one telling you this. But so Morishita, I think it's called Knots and Primes, just.
Okay. Okay, so this is in particular not just some simple. What isn't this a? Okay, this should be a finite group, or
no?
This is not a finite extension of Q. The thing that you wrote down.
I don't think so.
Okay, that is more in correspondence with the knot group than that. At least it's not finite. That was my first.
Yeah, it's big. I think these things get really big really fast. I mean, one fun thing that you can do. I mean, so that, if you like this sort of thing, I mean, you mentioned links as well. So you can look at, if you've got two primes, this is the sort of standard example that everybody loves. If you've got two primes, P and Q, then you're allowed to think about their linking number, mod Q, or mod 2. So look at their linking number, mod 2.
Yeah.
And that linking number, mod 2, happens to be the same thing as the Legendre symbol of P and Q. So this is, yeah.
Wait, how?
Here I'm oversimplifying slightly, but yeah, that's the.
You don't even know what the knots P and Q are, or what the knots corresponding to P and Q is. How do you calculate their linking number?
Well, so there's different ways to do it. So one way to do it is just to take, you cut out P from the thing. So let me assume, for the purposes of this conversation, let me assume
By
that
the
P
way,
and Q are.
one comment.
We think of them as knots. They're not actual knots, right? He's saying that in the analogy between knots and primes, the linking number is analogous to the Legendre.
I'm saying something stronger. I'm saying that these things really are knots and that you really are doing this computation.
Really?
Of the linking. Yeah, I mean that's the point of this whole picture.
So I think the quadratic reciprocity plays in or is built in really well. So if you just exchange P and Q, it's basically the same link with the same link.
Exactly. Exactly. Yeah. So if you, for the purposes of this, let me just say that let's assume that P and Q are congruent to 1 modulo 4, just so I don't have to try and get my signs straight.
Okay. So this is a fundamental discriminant.
And so now, so take P and cut it out of the thing. And now there's going to be a twofold covering of what's left over of the complement.
Mm-hmm.
And you can lift Q, the knot representing Q, up to that.
Mm-hmm.
And you can just compute the linking number sort of geometrically from that lift.
So, okay, is that somehow, okay, how do you still compute it? So now you have a double cover branched over the prime P, and you lift knot Q.
Yeah. And so so what do I have to say here?
Actually, okay, that does make, okay.
So the point is that you look at, after you did this, you look at the pre-image under the double cover of the other knot.
Yeah.
And this is the double cover of S1. So it's either just one S1 or two S1s. And whether it's one or the other is the linking number, not two.
I see. Okay, so the lift of P to the double cover is either two S1s or one S1. And
that's right. Yeah. And a fundamental geometric fact or homotopical fact is that if you take the linking number of P with respect to Q, then that's the same as the linking number of Q with respect to P, and that's just quadratic reciprocity for you.
Right. So
Okay.
in this book, Morishita notes and
yeah.
Okay, a similar question. So related to this thing, if you look at if you have a and actually where Kronecker symbol would play a role. So if you have an imaginary quadratic field, actually let's look. I wanted to understand that example better of Gaussian integers. So suppose you have Gaussian integers, then a prime in the ring of integers is either it splits or it's inert.
Yeah.
And that can be determined by the Kronecker symbol. How do you, I mean, that also means somehow the two knots are fundamentally different. So does the arithmetic topology somehow see this difference if a prime is split or non-split?
I mean, so this is, I mean, the tall homotopy type doesn't see the difference, but do I understand right? I mean, you're asking me whether or not if I take one of the knots sitting here inside Spec Z, and I look at what happens to it upstairs.
Yeah.
Yeah, I mean, there's a question of whether there's two knots mapping to it or just one knot mapping to it with a double cover.
No, wait,
so there's a link over it, and the question is, how many components does the link have?
Yeah. Do you buy that?
I'm sorry, in this case, we only have one knot. So let's take two primes in Gaussian integers, such that one is split and one is inert. How will the two corresponding knots? How will the two corresponding knots be different from each other, or this basically corresponds to the fact if the Kronecker symbol, so if the discriminant, let's say, well, the discriminant of the Gaussian integers is -1. If you look at the Kronecker symbol, -1 in the numerator and in the denominator, the prime. If it is +1, then it splits. If it's -1, then it's inert. So
But this is a prime. Sorry, I think I'm lost. So this is a prime in spec Z.
Yeah,
Am I making-
so I'm taking a lift of a prime from spec Z, from integers to Gaussian integers.
Right.
So any prime in Z would generate a prime ideal in Zi. Or no?
No.
I see
I don't think so.
5, for example, doesn't generate a prime ideal. It generates the product of 2 plus I and 2 minus I.
Yeah, so I would consider 5 as a split prime. Where it's
Yeah.
split,
So,
that's,
but I think, but that's the thing that I'm saying is that if you look at spec Z brackets I, you think of the 3 manifold there, and you think of the 3 manifold spec Z below.
Mhm.
You're asking whether you've got 2 separate knots lying over the knot.
I
Right.
see. Okay.
Yeah,
Yeah,
that's what makes it split or not split, whether you have a link lying over it with 2 components or not.
Cool. Okay, I was missing the picture that spec Zi and spec Z are also related to each other.
Yeah, right. You got to consider the map.
Yeah,
Otherwise, I don't think there's any kind of intrinsic way to see. Yeah, I think you have to have the map there.
Okay, cool. Okay, so next, thank you very much. This is extremely helpful.
Bet.
So the conclusion was this started with David Corwin's question. H1 of spec Zi, H1 et al. Of spec Zi is 3. Its rank is 3.
Ah, good.
So what is the rank of H1 et al. Of this thing? Yes.
You say this is rank 3.
I got this from conversations from you guys were having about.
No, this is 0.
Yeah.
This is 0.
It's H2 that's 4. And it's not
Yeah,
rank,
H1
it's size. I was asking about the size, just the number of elements of a finite group, not the rank.
Yeah.
Okay. So it's
And H2 is Z mod 4, right?
I see. So so these are just fully torsion.
Yeah. Yeah.
Okay. Do you have calculations for Eisenstein integers for these things? H1 and H2 of.
I'll be honest with you. I learned all this from Tomer. So Tomer, you have.
The answer for Eisenstein integers is 0 for H1 and Z mod 6 for H2. It's just this 4 is replaced by 6 there. It's really just the order. So if you have a totally imaginary quadratic number field,
Yeah.
whose class number is 1.
Right.
Yeah.
Finitely many example of those. I don't remember.
Yeah. 13. Yeah. According to Gauss, blah blah blah. Yeah.
Anyway, then the homotopy type is just the cofiber of from S2 to S2 of the number of roots of unity.
Of the number of roots of unity. Okay. Cool.
Either
Okay.
2, 4, or 6. That's it. So those are the options. So the Eisenstein one is going to give you.
Okay. So very good. So for the class number 1 case, it's completely clear.
The homotopy type is completely known. Yes.
Yeah.
And in fact, it's 2 in all other cases.
Yeah, it's 2 in all other cases. Exactly.
Okay, and H1 is different, or
note by the way, I just want to remark that the case 2, the thing that you get is the cofiber of the multiplication by 2 on S2, also known as the suspension of RP2, which is also the corrected homotopy type of Z that Clark defined, which also has exactly 2 roots of unity.
Yeah.
So it's
kind of creepy.
Put it in with the rest of the guys correctly. Yeah, I'm sorry.
No, that was.
So maybe I'll jump in here.
Yeah.
David, where are you gonna go?
No, go ahead.
Okay. I might have to go soon, so I messaged you this, but this was a great talk. Thank you.
Thank you.
I was just wondering, and maybe this is a better question for Minhyong, but so for example, if you take a local field, there are multiple there are local fields that aren't isomorphic but have isomorphic Galois groups. So I asked David this, but like my question is, so if you think of it in terms of field theories, like a topological field theory can't distinguish between them, I assume. My question is there like a non-topological field theory that would give you information about the difference, aka like ramification, filtration information. Does the question make sense?
I actually thought of a question just related.
I mean, it certainly makes sense. I guess the place that so this is something that I'd like to, so I know, so this is someplace where I would really like to have something like the Étale homotopy type or the stratified Étale homotopy type of the Farg-Fontaine curve, trying to distinguish those two different QPs, for example, or different locals. That's where I would try to, like, I don't know. That would be a cool theorem. I have no idea whether there's any hope for this, but it's.
Oh, the stratified homotopy type might tell you about the ramification or something, as opposed to just
of the Farg-Fontaine curve.
Yeah, of the Farg-Fontaine curve, not just of the spec.
Gotcha.
So.
Oh, that would be cool. That'd be very cool.
That would be. Wouldn't that be a great theorem?
Are the Farg-Fontaine curves
and then
different?
you could do other things over that base or something. I don't know. You could have your Reconstruction theorem maybe in a broader context.
Yeah. So I believe that this Reconstruction theorem holds for things of finite type over the integers. In fact, the things essentially of finite type over the integers. Oh, I have to. I always say that slightly wrong. I don't mean essentially of finite type, because I don't mean things that are. It doesn't matter anyway. So there's a sentence like that. But I don't have a complete proof of that sentence, but I think it's true. But I don't know what happens p-adically, for example, and I sort of feel like. Well, I don't know. I don't have anything interesting to say. I just don't have a theorem about anything p-adically yet.
Cool. Yeah. Thank you.
But I would really like to understand. I mean, I really feel like there's some work to be done understanding things like the homotopy type and stratified homotopy type of the FF curve. And I don't, as far as I know, no one's doing it. So I think there's cash on the table.
Guys, I have to go. I have to go to the daycare. It's closing in half an hour. Thank you.
Gosh.
It's 5 minutes away, but I should go. Thank you so much. It was awesome.
My pleasure.
I'll see you guys.
Good talking to you.
Bye bye.
Ciao.
So could I ask? Sorry, I had some questions, some of which actually related to Noam's earlier questions.
What's that?
Well, okay, so we were talking about like figuring out how to deal with the notion of something being a boundary with the Galois category. I mean, the common way to deal with schemes with boundary, right, is, well, either to use stacks like with Z mod 2 or log schemes. So I was wondering, have you defined Gal for stacks or log schemes?
For stacks, yes. For log schemes, no. I suppose that, I mean, I guess one approach to doing it for log schemes would be to take the, what do they call it? The inertial stack of the log scheme.
Right.
And then just take Gal of that. But yeah, for stacks and you don't need anything particularly cool about the stack. I mean, you do something totally naive. If you've got a simplicial scheme that's sort of presenting your stack, say, then you could just look at the sort of, like, it's the total category, if you know what I mean. So like an object here is a you know, it's a number, and it's a geometric point of Gal xn if n is your number.
Right.
And I mean, the maps are the things that you're going to write down first when you try to write down the maps. So yeah, it's just a category that lives over this thing. But I mean, you could also forget about this map, and that's the sort of the same thing as forgetting about the presentation of your stack.
You think of it as like the co-limit along the simplicial diagram of the Gals of the schemes.
That's right. Yeah. And there's nothing. I mean, the reason that's so trivial looking is because of the exodromy theorem, right? I mean, if you wanted to say that, you know, you want to say that functors from the Galois category of your stack into whatever perf should be the same thing as constructible sheaves on X valued in perf. But what is this? This is precisely given to you as a limit of the category of constructible sheaves on, you know, Xn valued in perf. So that's why this ends up just being that silly colimit instead of something more sophisticated. But yeah, so for log things, I don't know how you'd, I mean, I guess, what are constructible sheaves on log schemes? Are they the same as constructible sheaves on that inertial stack, or is it something more complicated?
I have to ask my Martin Olson about that probably, but
oh yeah,
I mean,
he'll know everything.
Well, especially about this, about there's the Kummer et al. Site and there's et al. Site. And
oh, right. There's this business about which site you're supposed to use.
But they give the same cohomology for nice enough schemes, even though people usually use the Kummer et al. Site.
Oh, is that right? I thought, isn't there some business with, oh, maybe that's only for like P torsion cohomology if you're working characteristic P or something.
That's something like, that sounds right.
There's some
This is
kind
just
of funny
there's an
issue
article
there.
with Kato that describes this pretty well.
Okay. All right. These are old memories and they weren't very good memories to start with. So I'm not sure I'm remembering anything correctly now.
See, my postdoc advisor knows a lot about log schemes, so I've been get a little bit.
I think I've heard his name in that context once or twice.
Oh, yeah.
Yeah, so that's a good idea actually, is trying to extract something that will be a functional, I don't know.
Yeah, I mean, I was sort of thinking about, like, you know, with Minhyong Kim's thing in general, like, can one get a notion of sort of arithmetic schemes with corners from maybe log geometry?
Oh, I see. That's a good idea.
Or a really long time ago, someone told me that a manifold with boundary is really just the same as a Z mod 2 orbifold. And so then schemes that would be, I guess, be a Z mod 2 stack.
No, but that's not gonna. That really uses the fact that you know, the essential fact that is no longer true in Tal homotopy theory of arithmetic things, which is that there's only two directions.
Yeah, right.
Right, like this Z mod 2 that you're talking about is the same Z mod 2 that explains why the double cover of any manifold is orientable.
Yeah, right.
Which is wildly wrong, right?
So very false.
So you mean it's pi 0 of R cross, basically?
It's pi 0 of R cross, yeah, which is, or better even to say, it's the unit in Z, which is not the same as the units in Z hat. That's the difference.
Right.
There's many more units in Z hat than units in Z. That's how you can get those twisting by roots of unity in the arithmetic duality.
Well, if you could do everything motifically, you get rid of you turn the Z hat into a Z.
No, it's not the same. It's not the same. It's really like the fact that in the arithmetic duality theorems, right? So, right, if you have a manifold, an arbitrary closed manifold, right? Then, and you're trying to write duality for local systems on it, then it's not necessarily a duality between, you know, the local system and its trivial dual. If the manifold is not oriented, there's an orientation bundle,
right?
Which
right.
Which has to do with a Z mod 2, with the fact the orientation bundle is a Z mod 2 bundle, and if you try to do the same thing arithmetically, you get the roots of unity, and it's really is not trivialized under a 2 extension. And that really has to do, like, the determinant bundle of the tangent bundle of spec Z is the inverse of the cyclotomic character. That's what this thing is telling you. And
I mean, if you did it motivically, be Z of 1 instead of ZP of 1, but either way, it's still non-trivial.
Yeah, it's still
right.
Cyclotomic character. This is and this is the same. It's exactly the same phenomena that in the client that what you get is a kind of a version of a Klein bundle instead of actually a torus for QP, in which when you go around, you get the P power. It's all the same thing. Those things are not Z-mod-2s. They are just not Z-mod-2s. This is an issue that I think Clark's approach is promising in the sense that he says, okay, let's construct it out of pieces that it is, but kind of forcing it to be completely topological has no chance of working. I think it's just not. Phenomenologically, you see that this is not a manifold in that sense.
Would you? I mean, would you somehow want a stack that has a profinite group as a stabilizer?
You can try to ask about it's kind of an orbifold with respect to z hat star. If you want to mimic this story that you said, you can try to talk about manifolds with a z hat star action.
That's what I'm asking.
I never thought about that approach. I have no idea if it would work, but that's definitely if you want to copy the Z-mod-2 idea with orbifolds, that's the
right.
I don't know. There's a right. There's a yeah. We do know what are, for example, right? Clark, thanks to your spectral Mackey functors, we know what Z hat star spectra are, for example. So we can.
You know what Z hat star spectra are.
So we can theoretically describe the genuine suspension spectrum of a manifold with arithmetic boundary using that. I don't know if this is going to be useful, but that's theoretically something we can do. And this is maybe less stupid than it sounds, because what the thing that you're encoding are essentially the geometric fixed points of this thing. If you take a geometric fixed point by a prime p, right?
You mean of the decomposition?
Inside of z hat, you take p.
Like ZP cross?
No, instead of z hat star, you take all the L's which are different than p. P is in there.
Yeah.
And in the ZP, you take 1. That's an element there.
Right.
And if you're asking somehow, what are the things that are, what are the things fixed by the orbifold? They're exactly supposed to. This is, I think, exactly needs to be the meridian of the. It's exactly the place in the manifold where you twist by multiplying by p. This is the p in the action of the tame inertia under the Frobenius inertia. So under the tame inertia on the Frobenius. So theoretically, maybe you can kind of use profinite spectral Mackey functor to at least describe the stable version of this, or something like that. I don't know. It's all very crazy. This is very late now. I'm probably not making it.
I had a couple more specific questions.
Yeah.
So when you were talking about whether you could formulate properness in terms of Gao, I was sort of wondering, maybe could you formulate the section conjecture somehow in terms of Gao, and then maybe formulate properness in terms of there are no cuspidal sections?
Yeah. Tomer and I spent some time thinking about that, didn't we?
Oh, really?
Unsuccessful.
Yeah.
Okay.
There's something kind of. I wish I had something good to say. I just don't.
Well, then I won't go too much further, because I imagine that you guys thought about it well enough.
Well, I don't know. Don't get discouraged by the fact we tried. Maybe you succeed where we didn't. But this is a very excellent question, which we actually spent quite a lot of time staring at the board and trying different things. And
why doesn't the evaluative criterion work? It's just a criterion in terms of morphisms. You have the same objects.
Well, so for example, so the point is that when you think about the evaluative criterion, it's a question. So let's do an example. So let's look at gal x over gal of the complex numbers. And so I'm trying to work out here whether or not this is proper.
Mhm.
So what the valuative criterion says, right? I mean, in the gal language, what it almost says is that, you know, if you've got a, you know, like it says that you can solve a lifting problem that looks kind of like that, right? But that's not, oh, sorry, this is the wrong way around. But that's no good. I mean, you can, of course you can solve a problem like that because this is just a point.
The other problem is that for a nilpotent, wait, no, what am I saying?
So it's sort of, I mean, somehow like once you pass to gal, you lose some of the,
Or it's too easy to solve the, okay, I see what you're saying.
it's too easy to solve the problem. Yeah. And so you need something that's going to pick up on the fact that yeah. So I don't know how to say this right, but you can say what you mean by a finite morphism of schemes in this Galois category language. But it's strange that you can't say what a proper map is, or at least it seems that you can't. The situation's kind of annoying. You know, there's a notion of a proper functor, and that notion. So what's the real story? The real story is that if you have a proper morphism of schemes, then you get what's called a proper functor, and that proper functor, that structure is good enough to do some of the things that. So for example, you can start trying to prove proper base change using the notion of a proper functor instead of a proper morphism of schemes. So that's something my graduate student Harry Gindy is doing. And then from there, you can start to try and build up the six functor formalism and stuff like that. And that stuff appears to be doable with this kind of weaker notion. But I don't know how to read off true properness of schemes from the Galois category side of things. It just doesn't seem. I mean, one thing to say, you know, one way to say what properness is that it's sort of universal closedness, but that universal closedness refers to taking pullbacks in the category of schemes, right? But pullbacks in the category of schemes are not pullbacks on the Galois category side. They're different. And it's a non-trivial issue.
Can I? Sorry.
Yeah.
Can I ask? Is like the Reconstruction theorem sort of related to, you know, the Stix-Schmidt article where they prove that every variety has like a Zariski open cover by sets that are anabelian with respect to the Étale homotopy type in some sense?
Mm-hmm.
And so is it almost just sort of saying that like the gal is sort of telling you the information about all the Étale homotopy types of sufficiently small Zariski opens inside your variety?
Yeah, I like that perspective on it. In fact, I'd really like to say the following. So, you know, there's an intermediate thing between the Étale homotopy type and gal itself, which I like to call gal x over p. So here I'm selecting a stratification, an algebraic stratification of my scheme, and I can work with this thing. And this is some kind of like family of delocalizations of the Étale homotopy type.
Right.
And it sort of ends with gal. But, you know, one of the things that's funny is that, I mean, as you know, the Étale homotopy type can have lots and lots of homotopy. And gal is just a one category. And so the question is that if you use one of these Artin neighborhood type arguments, can you eventually stratify enough so that at some finite stage, you're guaranteed to have a one category? And, you know, so it's easy enough to do it so that you're sure that all the strata are one types. You just kind of follow your nose. But I don't know how to deal with the links. I have no idea how to prove something like that. It would be really satisfying to have an argument that said that.
Wait. Wouldn't you kind of expect the links to be kind of sphere bundles over the neighborhood?
Mm-hmm. Yeah.
You mean you're thinking of like the compactification of the normal bundle of some closed subvariety?
No, not the compactification, the tubular neighborhood. The link,
Oh.
the link. If you have a smooth variety and a smooth subvariety, the link is just the puncture tubular neighborhood.
Yeah.
So it's a sphere bundle.
Right, right.
So in general, it has a pi n-1 when n is the codimension.
Yep. Sorry, yes, that's what I meant.
Yeah, and so the question is, can you always stratify in such a way that you can make sure that that M is 1? I mean, I don't know.
Doesn't the combinatorics of how they all fit together sort of matter?
Oh, but I don't understand. Wait, how is that will be possible? Like even if you take just a codimension 1, it's still it's an S1 bundle, then you're fine.
Yeah.
Oh, I see. So what you need is you need something which is both an art in both kind of at every level an art in neighborhood and it's kind of a normal crossing.
Yeah.
At the same time. Oh, I see.
Yeah, and I really tried to try and construct such a thing, like trying to kind of follow the SGA argument and sort of extract such a thing, and I just failed. Completely unsatisfying result.
And I just wanted to ask, I mean, I would imagine it might even follow from the proof of the Reconstruction theorem that sort of if you make P fine enough so that you sort of have anabelian neighborhoods, then you get something like the Reconstruction theorem just with some a specific P.
Yeah, that's right. So the Reconstruction, the Reconstruction theorem with a particular P.
Kind of. I mean, it's what I'm saying is not fully well defined. But the idea is that sort of if you fix two varieties and you sort of fix a P on both of them that makes everything anabelian, then you should get something like the Reconstruction theorem just with those, the gal X over P's.
So you're trying to combine what I'm doing with what the Schmidt and Stix do.
Yeah. Although I guess the problem is that you don't necessarily know that all maps of varieties are going to happen to respect.
That's right. You're going to only pick up the isomorphisms, I guess.
Right.
But if you, I guess that I would expect that to be true. Yeah, I'd expect that you should be able to, like for varieties over Q, smooth varieties over Q.
All the isomorphisms, because the isomorphism might not respect the stratification.
Right. So you're only going to get the isomorphisms that respect the stratification that you're writing down. That's right. But the idea would be that, I mean, if you have an isomorphism, then you can choose a stratification such that it will respect that.
Right.
And if you choose it to be an Artin neighborhood, then I don't know. I don't know how to formulate the right result, but I guess the thing that I would try and prove is something that says that you could reconstruct isomorphisms between between arbitrary varieties using a stratified form of Schmidt-Stix.
I mean, that would almost seem
normal
like
varieties.
It might almost be equivalent to that, just in terms of it's a sort of a limit question.
Yeah, I'm a little nervous though, because I just can't see how we can make sure that the links are nice.
Also, is gal of X, can that be expressed as some sort of limit over P, co-limit?
Yeah. Gal of X itself is the limit over P of gal of X over P.
Okay. Actually, I guess now that I have you, I don't know if I sent an email to you many months ago, but I was sort of curious about, for a manifold, right? Normally you do a stratified homotopy type for a fixed stratification, but could you do some analog of this sort of absolute thing? And I think I had a few ideas, but have you?
Yeah, I mean, my rough answer is I don't think so. I didn't answer because I didn't have a good answer.
Okay.
My rough answer is I don't know of a way to do that that will actually produce something meaningful. It seems, one of the things that happens is that you really are exploiting the fact that there should be a better way to say this, but the Étale topology is not like separable or anything. And so you're really kind of exploiting that fact. and I mean, anything that has any kind of like separation hypotheses is going to run aground with this. So more precisely what I mean is that if you take, so this, the way we construct our deleted tubular neighborhoods is the following. We use a construction due to Deligne called the oriented fiber product. And so, you take a closed thing and you take its open complement, and then you do a formal construction that you can do that produces for you the deleted tubular neighborhood. And this is the oriented fiber product. And if you happen to be working in a world where, where your Hausdorff, if these were Hausdorff topological spaces of any sort, really, this is always going to be empty.
Mm-hmm.
So you'll never see any of the stuff that you're trying to witness.
And for Z, you're sort of looking at the strict Henselian neighborhood.
Yeah, that's right. You take this and you thicken it up, and then you take the, but this, that's what the arrow up here does.
Spec of the strict tensillization of the local ring at that point.
Yeah, that's right. So you can think of this as sort of saying, I'm going to take Z, I'm going to factor it into, well, I guess this is really going to be, this is going to look a little funny, but I'll write it anyway. Yeah, so then first, well, I don't know.
I guess if Z is irreducible, you just take the point of the scheme corresponding to Z, and then take the strict Henselianization of the local ring at that point, which might not be a closed point.
No.
I think it's more complicated than that.
Okay. More complicated because it needs to map to Z. It's more like you're doing this is not a point. You're doing kind of a strict Henselization along the geometric thing, not along its generic point.
Yeah, and it only maps to it it doesn't map to it as a scheme. It only maps to it as a topos or something. Yeah.
But if it's a closed point, then you get what I just said.
Then you get what you just said. That's right.
Okay.
Even if it's not a closed point, but if it's a closed subvariety, it's different.
So yeah, I mean, and my idea for doing this for manifolds, I like maybe something like do a sort of manifold Zariski topology where the open sets are complements of closed submanifolds of smaller dimension.
Yeah, so I think in order to, I think you have to limit what kinds of manifolds you're looking at in order to make that work. So maybe you have to, if you add in set words like analytic in places, maybe you could get this to get off the ground.
That was one, I think when I wrote, I was like, well, maybe submanifolds, or maybe you have to do analytic submanifolds. And then I was actually curious, like to what extent the analytic Zariski topology, because can that compute the cohomology, ordinary cohomology of manifolds?
I don't know anything about that. Tomer, do you know anything about such things?
That's the analytic. I will be that. So essentially the question is, can you always find inside of an analytic manifold a bunch of closed submanifolds of codimension, some codimension that if you remove them, you're constructible? Yeah.
Yeah, exactly.
That is exactly the question, right? And the answer is that just take a Riemann surface, right? So it's the same, right? It's the same as the algebraic case. So the Zariski topology is extremely bad. It's confined. So in the simplest possible case, you see this can't work. So it's you have to choose, right? If your topology is if you're either locally constructible. It's somehow I'm unaware of any topology which is at the same time, stone and locally constructible. It's kind of not, you have to choose between the two.
Right.
Clark, I had a question actually. So because I was trying to think about what you were asking about the final certification, and we're trying to think about the inductive approach, and that kind of came to a more general question. So let's say that I have a map of algebraic varieties x goes to y.
Mm-hmm.
And I have a map from x to a poset q and from y to a poset p in a way that commutes.
Mm-hmm.
So is there a natural geometric condition that you can give such that the corresponding right? So I'm going to get a functor from gal xq to gal yp, right?
Yeah.
Is there a natural condition to put on this map endostratification such that this is a co-Cartesian fibration of Cartesian fibration? I need to think which one makes more sense, but one of those.
If you had said left or right, I might have had a better answer for you.
I'm sorry?
If you said left or right fibration instead, I might have been
better
prepared to answer.
Left or right fibration, I'm kind of seeing what it needs to be. But right, like
it's sort of a tall
proper or something like that. Yeah, but I think like if you look at the notion that appears in the development of art in good neighborhoods, which is essential geometric vibration.
Special geometric vibration.
Special geometric vibration. Thanks you, David. Right. So in this
that's
case,
Friedlander's terminology, but yeah.
So in this case, right, you exactly get something that looks like a family of things which are not smooth and proper, but they are stratified in a way which is kind of constant.
Right.
Right. You familiar with this definition, Clark?
No, but no.
Okay. So there's a notion that appears in this analysis of art in neighborhoods, which goes like this: you take a scheme S, and there's a map so you have a map from Y to S. Okay. And what you would want to give a condition that says that this map is in some sense homotopically constant, but you don't want to assume that it's smooth and proper. So what you're saying is that it's so the simplest possible example, but you can generalize this idea, is that you ask it to be smooth of codimension 1, and that it embeds into some smooth and proper map Y bar, such that the complement Z over S, or let's call it Z, it's a kind of closed.
Z is probably a better name for a closed, isn't it?
Yeah. Is a tile over S.
Yeah. No, I do remember this.
Finite
tall. Yeah.
Yeah, and the idea is that the thing that you're trying to encode is that you remove the same number of points, and you might move the point, and you might change the curve. And there's ways to generalize this, right? You can ask for a larger. You can say I want something with a smooth and proper compactification, such that there's kind of a divisor with normal crossing, which is smooth and proper over the base.
And then you basically all of the intersections are also smooth and proper over the base.
Yes. So this
I think the higher dimensional version is Friedlander and not Artin.
That's true. And Friedlander defines this notion to get the condition to have a fibration of homotopy types. Right. That's the condition. This is how you get the fibration of homotopy types.
I see.
Without assuming smooth and proper. And that's kind of the way you have this, but you can rethink about. So here's my point. Here's another name that you can give to Friedlander's fibration theorem. So Friedlander's fibration theorem tells you that if you have a map from Y to X that satisfies this property, and you choose a fiber and the base is connected, then you have a long sequence in homotopy groups.
Absolutely, right? Yeah.
And if your Y is smooth and proper over the base, then that's essentially an algebraic version of Escher's theorem.
Of what? Sorry.
Escherman.
Right. Erisman.
The differential topology theorem. That if you have a proper submersion, then all the fiber are homotopy. It's a fiber bundle.
Yeah.
And what I'm trying to say is that one way to, if you want, the thing that Friedlander is doing is just erasing those points. But if you want to think about it a little bit differently, what he does is actually stating a stratified Erisman theorem. Right? Because clearly, instead of taking of the homotopy types, you're just going to you take the induced stratification, the induced stratified homotopy. This is also going to be constant, right?
Yes.
Run. Thanks, y'all.
Ciao. See you.
Ciao.
Now you can be even slightly more sophisticated than that, right? So that's not a left vibration. That's already something better. But this is over a base in which you think of the base as an infinity groupoid. So this is kind of a local system of categories. But you can try to be a little bit more well-behaved, kind of, and you can ask, what if I'm allowing, usually when I have an algebraic map, I have singular fibers, and I'm forcing you to stratify those fibers. So I think I have an intuition that being able to answer this question, what is the kind of generalization of divisor with normal crossing, quote unquote, which is a condition that will force this to be a co-Cartesian fibration, which would tell you that this Galois category actually, you can think about the fibers, you can kind of unstraighten this and get the Galois as parametrizing the stratified homotopical of the fibers. That would probably, if it's possible to write such a general lemma, I think it would be very, very useful for those kinds of questions.
No, so but this is, I think this is related to the stuff that that Harry's been thinking about. So here's how. So it all comes down really to kind of Quillen's theorem B. So if I think about this, what's that?
I don't remember which one is B.
B is the one that says that, if you've got a functor between two categories, and you look at the over category and take the fiber product with this thing. If all of those are the same, then those are actually computing the homotopy fiber.
If all of them are the same, they compute the homotopy fiber.
Right, so you do this kind of thing. So you look at gal of, let me do it this way around for reasons. And then you look at the fiber product. I'm not going to try and, I guess I'll call it gal x y over, even though that's bad notation. And if, for any map between the two y's, if these things are the same, then this is the homotopy fiber of this map. That is to say, when you look at the nerves, this becomes a fiber sequence.
Yeah, okay. Oh yeah, this is what he called, Quillen calls it quasi-fibration is a fibration or something like that, right? That's the
Yeah.
Okay. Yeah, okay. No.
He uses this for algebraic K theory, right?
Yeah, this comes up in algebraic K theory. That's right. But there's a story here, and what's the story? The story is that you can ask for a condition on this map such that if you put y in here and you form the pullback, I'm just going to write gal x sub y here. So these are both pullbacks. That if you do this, then this is cofinal in whichever direction I mean right now. So this is the condition. So depending on which of these things you use, I guess the way that I've written it here, this is the condition. This is weaker than being, this is smoothness. This is smoothness of a functor rather than of a morphism of schemes.
I'm confused. What do you mean it's a smoothness of functors?
There's a definition in higher topos theory of what it means to be smooth, and
you mean
it's roughly speaking this.
Oh, that's very interesting. But do you mean when the category that you consider is the category of constructible sheaves?
No, the literal category gal that we're writing down here.
Oh, that's the definition of a functor from being smooth in that sense.
Yeah, and what does it guarantee? It exactly guarantees that functors out of it satisfy the smooth base change condition. That's the literal definition. Like that's what you unpack when you write down the definition of smoothness of a functor between categories. So what does that mean? That means that if you have any morphism of schemes that induces a smooth functor in that sense, then it will satisfy the smooth base change theorem. So what are the, let's write down what the objects are because we can. So this is just the strict Henselianization. This is just sort of the localization, y localized at y.
Mm-hmm.
And so, this is really including the special point into the strict Henselization of y at y. But the real hard part here is actually understanding what the heck this is. Because this fiber product doesn't agree with necessarily the fiber product of schemes.
Yes.
So the hard part is really understanding this and really getting a grip on that. But it seems to be the case that, so that's smoothness. There's the dual notion of properness. It appears that smooth morphisms of schemes give you smooth maps of categories, and proper morphisms of schemes give you proper maps of categories, at least in good situations.
Well, that's phenomenal.
And so then this is like a completely like sublimated version of smooth and proper base change.
So is the definition of smooth and proper in these cases essentially that smooth and proper base change holds in a universal sense?
Yeah, that's exactly what it is. And you know, modulo this sort of irritating thing that we can't compute very well fiber products of, like, I don't necessarily always have a scheme theoretic interpretation of these fiber products of Galois categories. Modulo that, that's these things really match up perfectly.
Oh, but that's great because that's giving you more generalized schemes.
Right, that's right. So the other thing that this does is that we haven't exploited yet is, you know, in the same way that in the Klaus and Schulze stuff on condensed mathematics, they have a way of creating a canonical compactification of a scheme so that you have coherent duality in this very functorial way. These categories appear to have canonical compactifications too. I mean, you can really just sort of factor your scheme into an open immersion followed by a proper thing in a canonical way, in a functorial way. And so it seems like you should have access to the same kind of conceptual power. Like if you want to construct the 6 functors, you know, that seems like a really good way to do it. We haven't done that yet.
So in particular, but you're also going to get, right, if I understand correctly, for example, Arithmetic theorem, you're going to get it here, right? It's if you have a smooth and proper map, then all the homotopy types in the fibers are going to be the same.
That's right. That's exactly right.
That's really cool.
Well, one thing I just want to mention is that about the thing about having a fibration that's not actually proper is, more generally, you don't want to require there to be a compactification, but that locally on the base you have a compactification, right? Like a special geometric fibration means that you have a smooth map that has a smooth proper compactification where, you know, as we were saying, like the boundary satisfies the right conditions of being smooth over the base.
Yeah.
But then more generally, a geometric fibration is one that is locally on the base, a special geometric fibration.
Oh, I see.
And I've been wondering if there's like a theorem that like any torsor under a smooth group scheme is a geometric fibration.
What do you say?
So actually, this is a question: is any, if you have a map that's a torsor under a smooth group scheme, I mean that should be a you know, fiber bundle topologically. And so the question is it always a special a geometric fibration, and that's Zariski locally you can compactify it in the right way?
I don't think so. I think those are kind of, I'm not an expert, but I think those kind of hard questions that have counterexamples. You're asking about essentially about equivariant compactifications, which is kind of a.
Are you characteristic 0?
Say characteristic 0.
But you want it to be smooth, right? So you can compactify it, but you want to compactify equivariantly.
Yeah. And I'm allowed to take a Zariski open cover of the base. Like I just want to do it locally, equivariantly.
Yeah. It's not like I'm. My only reaction to it is I remember that I kind of have I don't know anything about it, but I remember it to be, you know, something that's kind of in. I think like you can, you know, all kinds of kind of geometric invariant theory issues come up and things like that.
You could ask one of the like Dan Abramovich or someone who does resolution of singularities. They might.
again, I don't want to be. I think if I remember correctly, like definitely Hironaka's argument is not equivariant. Like you don't. Right?
Yeah.
It's very.
I mean, really, what I care about is just that to know that if you have a torsor under a smooth group scheme, that it gives you a fibration on identical homotopy types. In other words, that the homotopy fibers are the same as the étale homotopy types of the geometric fibers.
Yeah, so I think there's ways to prove that, but I don't think that's the way to do it. I think what you would probably want to do is.
Shouldn't you just be able to push the fiber around with the group action?
I'm sorry?
I mean,
Oh, never mind. Maybe I'm saying something stupid here.
That doesn't let you get between fibers.
So what I would do is that if you extend your world to simplicial schemes, you can write this thing as a pullback of
Oh, I see.
X goes to BG, and I think that would be a better way to try to do that.
Yeah.
Okay.
And the point is that there's kind of a canonical trick that you can apply in those worlds, because you take your cover, your G cover, and you write. So the first thing you do the check construction. But then, because it's a torsor, it's isomorphic to removing a copy of G level powers of G, and then you collapse one coordinate. That gives you kind of a completely algebraic.
You're talking about the fact that it cross itself is the same as it cross G.
Yeah, and you do it again and again and again. So the check construction gives you y times G, y times G times G, etc., etc., etc. And then you collapse the y, so you get a map to the canonical version of BG. And if you see what the fiber is, you immediately see that it's the constant y, because at every simplicial level, what I did, I collapses the product. So what you get, you do a simplicial resolution level-wise, it's just a projection of a product, and then it's a fiber. That's what I would do to put something.
But I think something like that is actually in Friedlander's proof.
Friedlander's proof, if I remember correctly, just kind of uses the property of the you're showing the state, this classical statement about push forward of cohomology, that in this case the push forward of cohomology is a local system.
Yeah.
And then it's kind of a Hurevich philosophy to.
You're showing the homotopy equivalence by showing it on fundamental groups and on cohomology with coefficients in any local system.
Yep. That's
there was something about a BG and
maybe I don't remember. I am going to sleep. It's very late, and tomorrow morning I'm going to be very early.
By the way, can I quickly say, Tomer?
Yes.
At some point, I don't know if you saw my email about the stuff about cuspidal sections.
I seen. We're going to talk at some point.
I understand. I just wanted to remind you. It's basically it's something where I feel stuck, and I feel like at some point you told me that you saw how to do it. So.
Okay, I'll.
Eventually, I understand. I just wanted to. I assume you are busy. I assume that's why I haven't heard from you other than.
I am somewhat busy. Yes. And Clark, you seen the email from me just yesterday.
No.
Regarding Omer.
Oh yes, I did get that. Yeah, thank you. Yeah.
Great.
Will do. All right. I'm off too.
Quick question.
Oh, yeah.
Is there this stratified homotopy seminar?
Oh, that thing. No, that sort of just has turned into me supervising Harry.
Because at one point Harry told me that he was going to see if I could join it, and then he was suggesting that I ask the questions that I'd emailed to you in that seminar, and then.
Yeah, I mean that was going on for a little while, but it's it sort of narrowed down until it was just me and Harry. So. But
now it sounds like, if I understand correctly, you did actually look at those emails I sent. It's just you didn't respond because you didn't have any.
Yeah, I mean it's there's something kind of depressing about writing an email that says I have no idea what the answers to any of your questions are, but
I just wanted to know.
It's very hard on the psyche to have to say I don't know so many times.
And I guess did you see the thing about just like the question about doing a tall homotopy obstruction sort of in stratifications? Because like I was very fascinated with this idea of a stratified a tall homotopy type because of all the discussion of stratifications in my paper with Tomer.
Oh, I don't remember this point exactly.
Should I just like re-forward that email to you?
Yeah, would you?
Yeah, sure.
That sounds interesting. I'll look at that.
Yeah,
and then I can't
just
remember. I must have looked at it, but I can't remember anymore.
Yeah, and then I mean, I'd love to talk. Whenever you do have time, talk about like arithmetic topology stuff. And I'm sort of curious what you've been doing with Tomer in terms of like replacing the places in infinity, because I'm very interested in the whole how to deal with the places in infinity.
Yeah, I mean, I think there's some really cool stuff that can be done there. I don't have. Well, yeah. Let's talk. We should absolutely talk.
And I could also tell you about Denninger's dynamical system at some point.
Right. I want you to educate me on that, but I'm going to have to do so. I'm going to have to do so on a day when I've really slept, because I remember looking at the paper and feeling like, oh man, I'm out of my league here.
I know what you mean. Okay, but I just want to. So we'll at some point in the future when we both have time, we should talk about stuff like that.
Yeah, I mean, things should start opening up for me, like in December.
Okay.
While I'm still teaching, it's going to be a nightmare. But I really hope that in December we can probably get together and chat. Virtually.
Perfect, because I have a lot of postdoc applications due in early December. So.
Right. Yeah. So that'll be perfect then. So we'll talk around.
Do you like being bugged? Like, should I send you an email then in December?
Yeah, pester me via email, and we'll figure out a time.
Email's good. Okay.
Cool. Yeah, that works.
Okay, I wanted to get a plan. Okay, see you. Thank you so much for the talk. It's really great.
You bet. Thanks. See you soon. Ciao.
Oh, question?
Yeah.
Is there a motivic stratified homotopy type?
I don't know of one.
Okay, but that's like an open thing where one could.
Yeah, I mean that feels like a place that you got to figure out what the hell to do with A1, right? That's the hard part.
Right. Because it's supposed to be contractible, or is it?
Yeah, I mean it's kind of weird to think of it. See, I've always objected to that. I mean, in characteristic 0, it's fine, but in characteristic P, why is it really contractible?
Well, there's this. It's not.
I mean, it certainly isn't from the Attal point of view, right?
Right. There's this
Every
like
quasi P
theorem.
group appears.
Yeah.
As a quotient.
There's this theorem that like anything in characteristic P with a trivial Attal homotopy type is basically spec of FP bar.
Yeah. Yeah.
And see, when I search the term stratified homotopy theory on Google, I get Peter Hain. So is that something that you guys invented?
Yeah.
Oh, okay.
Yeah.
That's what I was.
Yeah, we just invented it. I mean, there's nothing else to say. I mean, so there's an old paper of Quinn, I think, where he's trying to develop it, but it's it's hackneyed and it doesn't work in algebraic contexts. But now that we have this picture from Hain, it's
because the way you said it, it almost sounded like maybe you were relating it to some previous concept known as stratified homotopy theory, and that just helps a lot for conceptual understanding.
Yeah, I mean, so I guess people believed that what a stratified homotopy equivalence should be is something that gives you an equivalence on strata and links. That's what they thought it should be. Mm-hmm. And what Peter showed is that if you take that notion and your stratified spaces or topological spaces are reasonable, then that actually just gives you the homotopy theory of infinity categories with a conservative filter
category that I guess Lurie had defined.
Yeah, exactly. Oh. So the exit path category is an equivalence of homotopy theories.
Right.
That's the point.
Perfect. Random other question: Are you at the same place as Jonathan Pridham?
Yeah, in Edinburgh. Yeah.
Right. Okay.
Yeah.
I just realized that you were both there.
Yeah.
He does a lot of cool like arithmetic and homotopy stuff. So.
Yeah, I wish I could understand anything he was saying.
Oh. I was just asked to referee one of his papers, and I said like I don't have time or enough knowledge, and I'm just like
interesting.
That's like if I had time, that's like exactly stuff that I would love to learn more about.
Right. There's only so many hours in the day. Yeah.
Right. Okay.
All right.
I'll let you. I'm sorry. See you. Thank you so
soon.
much.
No. Ciao.